So I'm going to talk to you about this topic, the virtue of complexity, which is joint work with a frequent collaborator of mine, Semyon Malamud, who's at the Swiss Finance Institute in Lausanne, and one of my PhD students at Yale, Kangying Zhou. I'm going to start with a little bit of the background that ties in with some of the comments Alexander was making. So on the slide, I have reference to two massive statisticians from the 20th century, John Tukey and George Box. All right. So Tukey introduced this idea of the principle of parsimony. I think about this principle as sort of the guiding principle for my era of econometrician. When I was trained, we were trained that parsimonious is better. All right. So Tukey actually articulated a particular principle of parsimony, but I actually like George Box's way of thinking about it as being a bit more transparent, and one of the leading textbooks from this generation, right, time series analysis, forecasting, and control, has as its cornerstone idea for how you build forecasting models. It is important in practice that we employ the smallest possible number of parameters for adequate representations. That's their emphasis. All right. Now, I bring this up because the premise of this conference, the idea of AI, ML, and finance, really clashes with this idea. And we need to think about how to reconcile this, all right? So just to give you a couple of examples, modern ML algorithms, GPT-3, this is one of these state-of-the-arts, is actually in the process of being displaced already, but this has 175 billion parameters, a leading NLP model, right? 175 billion parameters. All right, I have a very sort of tiny model by comparison where I use a neural network to forecast stock returns at the monthly frequency. I don't know, to empirical asset pricers, this is a huge model with 30,000 or more parameters in this model, okay? All right, now, so if you're thinking about this from the perspective of the Box-Jenkins lineage, right, this sounds crazy. Not only are these parameterizations profligate, they're probably going to massively overfit your data, which means that they're probably going to be disastrous in forecasting out of sample, right? That's the Box-Jenkins way of thinking about things. That's how I was trained, all right? Now, this is wrong, and that's the entire point of this talk. This way of thinking is actually wrong. In fact, some of these models that I've referred to here, they have astronomical parameterizations, yes. They overfit the data, yes. In fact, in sample, all of these models, they actually exactly fit the training data. No error in the training data. These are the models that we expect to do really poorly out of sample. Turns out they're the best performing models out of sample. All right, so evidently, modern machine learning seems to have turned this principle of parsimony on its head. And we need to think about how should we be approaching finance problems with this knowledge? There are these very important domains like image analysis, NLP, where massive models dominate simple models. You can show very clearly that parsimony is bad in these settings. You want to overfit. These models do well out of sample. How could that be? Why could it be? Now, before going into sort of an explanation for how this can be and why it can be, I want to point out that this is happening in finance too. It is not just the case that in image recognition, profligate models perform well out of sample. It's true in finance, right? So there's a very recent big literature. Some of these papers by people in this room, I've written these papers, people like Stefan Nagel have written these papers, where we use big models to try and do things like forecast returns or to build stochastic discount factors, optimal portfolios, right? These models do well out of sample, and they do better than simple parsimonious models, right? So it's interesting, this literature is growing very rapidly. There's a ton of interest in it, right? But there's also a lot of pushback, right? There are a lot of skeptics. This can't be true. You've overfit the data and you just kind of got lucky out of sample. All right. I think part of this pushback and the skepticism is rooted in the fact that there's not very well developed theoretical understanding for the statistical properties of these massive models. All right. So that's what I want to drill into in this paper. So you can think of what I want to accomplish in this paper as being, I want to build the case for doing machine learning in finance. All right. In order to do that, I think we have to understand the theoretical statistical underpinnings of these massive models. All right, so that's what I'm going to go after here. And I'm going to show you, I think, some striking results that line up very closely with what we've seen in, for example, neural networks applied in these non-finance domains. In particular, I think the most important result I'll show you is that if you do kind of an apples-to-apples comparison where you start with very small models and gradually make the models richer and richer, more and more parameters, you should expect to see a continually increasing out-of-sample Sharpe ratio for a strategy that uses forecasts from those models. All right, so I'm going to focus on trying to explain the intuition and along the way kind of answer the skepticism, understand why it is that these big models can work well out of sample. But it does rationalize the prior evidence that we've already started to accumulate in finance, that these big ML models are useful and they outperform simple models. All right. In addition to that, once I show you kind of the basic theoretical properties of these large models, I'll show you kind of exact analogs in data applications, very standard data applications that we've been studying in finance since, Schiller-Campbell style predictive regressions. And you'll see that these patterns arise very naturally in that data as well. Okay, so unfortunately, I do need to take you through a little bit of math for this talk. All right, so I'm going to start, you can think of it as a thought experiment. All right, I want to imagine an analyst that's doing a research project, trying to forecast returns, R. That analyst has access to some predictive variables. I'm going to call those G. G can be anything you want. Think of it as, I'm happy thinking of it as a relatively small number of predictor variables. The important aspect of the predictive relationship, though, is that I don't know how G forecasts are. I believe it's predictive, but it may be predictive in complicated, nonlinear ways. All right. Now, an important premise of this thought experiment is to put yourself in the mind of the analyst. Does the analyst know the functional form for F? Have I ever worked on a prediction problem in finance where I knew the functional form? No. It's totally implausible to think that an analyst knows the functional form of their prediction problem. So how do we proceed? Well, there's only one thing to do. You write down a model that you hope approximates the truth. Now, this is where machine learning comes in. One way to kind of think about maybe even defining machine learning is a set of models for approximating generic functional forms. So I could say, listen, I don't know F, but I know a lot of good models for approximating F. Take, for example, a neural network. I don't know how G is going to flow through the neural network to get to R, but I can approximate it. And the way that I do that, it really actually ends up having a fairly intuitive and straightforward form. What I'll do is I'll take all of that information in G, I'll propagate it through an artificial network. And as it propagates through that artificial network, it gets mixed together. So nonlinearities start to get picked up, interactions among the variables start to get picked up. And on the other end of the network, you get a bunch of transformations of this original predictive information. But what always happens at the end of a neural network is you run a simple regression. And that's the way I'm going to be thinking about this. So my S's here are going to define my empirical model. S's are my original data propagated through a neural network. I get it out the back end, and now I run a regression. I'm going to regress returns onto whatever these nonlinear, potentially complex transformations of my original predictors are. All right? This is a very realistic way of thinking about how model specification happens for finance research, for asset pricing research, for portfolio management. This is how we attack these problems. All right. Now, this is just a setup of the formulation. What's the real problem that I need to answer? What is the question that I'm going after? Okay, so I have my true model. That I don't know. I have my empirical model. It approximates the truth. Now, one thing that we need to recognize about neural networks is that the more terms I have on the right-hand side here, the more terms I have in the sum, the better the approximation of the truth. All right? That's just basic non-parametric statistics. If I put more approximating terms in my model, I get closer to the truth. So now the analyst has to ask a question. I have a fixed amount of data points, call it T. How many terms should I have in this approximation? It's not at all obvious ex ante. George Box would say you should have a small number for P. All right? Machine learners, people like Yoshio Bengio, These people that are pushing the envelope with these massive models say, no, make P very large. Who's right? Well, we can think through some of the trade-offs here. The trade-offs are actually really straightforward. If I have a simple model, so P is very small relative to the number of time series observations I have. Imagine you're doing return prediction where you have like 100 months of data. You might feel comfortable using 2, 3, 4 terms in this regression. You can estimate parameters in a model like that with relatively low variance. Okay, so what's the trade-off I'm facing? If I use a small model, I estimate parameters, and those parameters that I've estimated have low sampling variation, which is exactly one attribute that I'd love to have when I go out of sample, right? I like parameter estimates that are stable. Small models get you that, but small models give up approximation accuracy. So when I think about going to the complex model, that's exactly the benefit of using complexity. I get good approximations. But the problem is I have to estimate all those parameters along the way, and that costs me variance. I end up with highly variable parameters, and when I bring those out of sample, they may potentially disrupt my forecasts. All right, so that's the question. Which P should the analyst use? How big of a model should I pick? The answer is kind of surprising. You should pick the largest possible P your computer can compute. That's how big of a model you should use. You will always end up with better out-of-sample performance in expectation, out of sample. You will end up with better performance with the larger model. And this paper goes through the theory to support that. All right, so what I'm going to do now is I'm not going to take you through the theory. It's a little bit of a bear to get through that math. But I'm going to give you a little bit of a framework to just help you think about what end up being really straightforward and intuitive mechanisms at play in the statistics. All right, so in order to start making progress on this, we can start really simple. We can start with OLS. When I run regressions, I'm solving systems of equations. If I have T observations, I have T equations. P is the number of unknowns that I'm trying to solve in those equations. All right, so when I have small p, I can hone in on a set of parameters that fit those equations as well as possible. And they tend to be low variance when I use a lot of equations to identify a small number of parameters. It's interesting to think about what happens when t gets very close or even equals p. I can actually still do OLS when I have exactly as many parameters as I have observations. When I do that, there's one unknown for each equation. I can solve that system. In fact, that's a really interesting solution because what it does is it exactly fits my data, just like those neural networks that I was talking about before. Now, we tend to think that models like that behave very badly out of sample. All right, and in OLS, it does turn out to be the case that these models often do badly out of sample. But what's interesting is that I don't have to stop there. I don't have to restrict myself to looking at only models where p is less than or equal to t. I could start to use, if I have t equals 100 months, I could use 1,000 parameters or 10,000 or 1,000,000 parameters. I can estimate that system. Now, go back to thinking about it as a system of equations. When you have many equations, but more unknowns than equations, what happens? You have multiple solutions to fit that system. All of those solutions will exactly fit your data, all right? So you as the researcher, as the econometrician, have to start making some choices. Which of those solutions do I want to pick when I go out of sample to forecast? Okay, here's where we're going to get a little bit technical in the math, but this is going to really be the extent of it. When p is greater than t, we're going to pick very specific types of solutions that exactly fit the trading data. Okay? We're going to pick solutions that have small L2 norms. What does that mean? If I have an infinite number of possible least squares solutions, ridge regression is always going to pick the solutions that have small variance. It's like when you're doing theory and you have to do some equilibrium refinement. All you're doing is saying, I have a lot of options at my disposal. What's going to be my decision rule? The default decision rule, if you're doing least squares, is really ridge regression. And in this case, the default rule is, of all those solutions, pick the one with the smallest variance. It makes really natural sense, right? We want to go out of sample, and we want to have reliable, stable forecasts out of sample. So we're going to do that. But note that even when I do this, I'm still going to be able to work in an environment where I exactly fit the training data. Okay, so I'm going to call that, actually, I'm going to give that a name. I'm going to call it ridgeless regression. Ridgeless regression is when I run a ridge regression, choosing the penalty so small that I exactly fit the training data, but I choose the least variable possible solution, the least variable possible beta estimate for when I do my out-of-sample forecasting. All right. Now, with that background in mind, we can talk about the theoretical relationships that appear out of sample and that we derive in this paper. All right. So I'm going to introduce a term here, C. C stands for model complexity. It is just the number of parameters divided by the number of observations I have in my training data. All right, when C is very small, this is like traditional econometrics. C is close to 0, right? That's what we always have when we do traditional econometrics. We always use limit theorems, asymptotic theory. It actually forces our C to be 0 in the limit. What I want to talk about in this paper is all the behaviors of models when C is very different than 0. That special case when the number of observations exactly equals the number of parameters you're trying to solve for, that's C equals 1. I've given it a dotted line here. It's a very special occurrence. Now, one thing that we get from this kind of OLS background that we were going through on the previous slide is if I start with a small model, I'm going to have a low volatility trading strategy based off of that model. If I estimate that beta and then bring that beta out of sample to build portfolio weights, if I have C close to 0, so I'm not estimating many parameters, the beta is going to have low variance, as we typically get with a small number of parameters. And when I go out of sample, the volatility of that trading strategy is going to be low volatility. I'm not saying whether it's a good or a bad trading strategy, but it will be low volatility. Now, what happens is I start to increase the number of parameters. And in particular, what happens when I start to get close to the number of observations? Well, this is the case where we all know that OLS blows up. If I have exactly the same number of parameters as I do the same number of observations, that's actually the maximum variance estimator you could sort of get out of doing least squares. That's the worst case scenario. In that case, there's only one solution, and you know it's going to be high variance. So you kind of want to stay away from having to estimate parameterizations with C close to 1. But what's really striking about this graph, and where you should be paying most of your attention, is what's going on out here. As I make the number of parameters much larger than the number of observations, for example, 10 times larger, I actually end up with a low variance trading strategy again. How does that happen? Well, it happens because when C is greater than 1, again, I have many solutions that possibly fit the data. I'm going to pick the one with the lowest variance. I've exactly fit the training data, but at the same time, I had the flexibility to fit the training data with a model that's going to be low variability out of sample. Now, why is it that actually this variance is coming down as I increase model complexity? That is kind of intuitive as well. As I increase the number of parameters, I make that original system of equations less and less well determined. The space of solutions get bigger and bigger. So I can always find a model, an estimate beta, with lower and lower variance as I have more and more complexity. All right, so the first key takeaway when we're thinking about model complexity is that it's really straightforward, it's really unambiguous. If I make my model very large, I will end up with low volatility trading strategies associated with that model. All right? Now, what happens to the performance of that trading strategy in terms of expected return? Here it's a little bit maybe less obvious what's going to happen. If I start with a very simple model, one thing I know is going to be true. It's going to be a poor approximator. I know that if I add more and more terms to my model, I get a better approximation. So the problem with using a small model, yeah, it gives me low variance, but it also gives me low expected return because it doesn't forecast well out of sample. It's so far from the true data generating process. It can't give me a good ER. Now, as I start to increase the complexity of my model, here is where the approximation benefit kicks in. Notice, in the volatility picture, there's no benefit from having a better approximation. It's all about the variance of the estimator. So where does the improvement in approximation and the benefits associated with that come in? It comes in terms of ER. As I enrich the complexity of my model, my expected return out of sample gets better because I get a more and more accurate approximation of the truth. All right, these two pictures here are the core of everything there is to understand about why trading strategies perform better going out of sample. All you have to do is recognize is if I increase model complexity, I can build a low variance strategy. And as I increase model complexity, I get a better approximation, so the ER goes up. What does that imply? Well, obviously, it means the Sharpe ratio has to be increasing in model complexity. All right, so this is the main theory result. The expected return is always rising with model complexity. That's an unambiguous point, and it should actually feel like a fairly obvious point. If I have a more accurate approximation of the truth, I can trade more effectively on that information. And that's true on an out-of-sample basis. The trade-off for that is about variance, but the key is that we spend so much time thinking about variance in this low complexity regime or when P gets close to T, that we sort of miss the point that if we look at these very big models, the trade-off is, again, unambiguous. You always want to have a big model. Complexity is a virtue. Here's another way of pitching that original question that the analyst is asking. If the analyst is sitting there with some model size P, they ask themselves the question, as I add one more parameter, is it worth it? Is the gain in approximation benefit dominant relative to the cost of the variance that I introduced into my model? That trade-off is explicitly solved here. It tells you that for any P, you always want to add that incremental parameter. The benefit of improved approximation overwhelms the cost of additional variance from having to estimate that new parameter. That's what this entire trade-off boils down to. I'm showing it to you in a finance context. So I've translated all of this into economic quantity, the economic terms of an out-of-sample trading strategy performance. But these results, they also hold if you're talking about NLP models where you're trying to predict the next word that a speaker is going to say. Holds for image recognition where you get a new image and you're trying to determine whether or not there's a cat in it. Right? Bigger models will always have these properties where you're making this trade-off between additional approximation benefit versus the cost of higher variance. These very high approximations will always lead you to prefer these large models, and this is why you see all of the neural networks that are applied in Silicon Valley using many, many more parameters than we have observations to train on. All right, so I've shown you pictures to make this argument. I've tried to provide some intuition for making this argument. I do want to point out that this paper provides a general and rigorous theoretical derivation for this, all right? The plots that I've shown you are calculated from those theorems. I've used a calibration that essentially aligns with some empirical problems in the literature, the idea of forecasting monthly market returns. So now what I want to do is I want to move to looking at some empirics. Now that we see what the theory plots will look like, what do we see actually apply this type of comparative static in the data? All right, so I'm going to analyze the exact same types of plots that I just showed you for theory, but I want to do it in data. So which data should I use? I'm going to focus on what I think of as a cornerstone of empirical finance, forecasting the aggregate market return. Right? I think there are two cornerstones, right? You forecast the market return or you predict the cross-section of returns. We're starting in this paper with the first one. Now, I want to make the conclusions also easy to digest, so I want to study a conventional setting. Well, we have some great conventional settings for this. We have the crisp valuated market return, the standard forecast target, and we have a standard set of predictors. I'm going to use the Goyal-Welch predictor variables, which include kind of all the usual suspects, inflation, dividend yields, market volatility, interest rates, and so forth. All right. Now, in order to actually conduct an analysis like I do in the theory, I need to be able to vary the complexity of a model from very simple to very rich. And that's not easy to do with 15 predictors. But the point is, in the theory, we're not thinking about the number of observations as being the number of distinct predictors. It's actually about the number of nonlinear and interactive expansions of those original predictors, right? I want to take those 15 Goyal-Welch variables and propagate them through a big neural network. And when I get the final nodes, I've mixed together those Goyal-Welch data in really complicated ways and produced hundreds, thousands, maybe even millions of predictor variables from those original 15 variables. There's a beautiful approach to doing this from the machine learning literature called random feature regression. Essentially what you do is what we did in the theory. You take your original raw predictors, G, that's the Goyal-Welch data, it's like 15-dimensional. You take a random draw of 15 weights to combine those predictors. That's a normal variable, omega. And then you feed it through a nonlinear activation function. It could be your standard ReLU. It could be a sigmoid. Here we use a sine function. Okay, so it's called a random Fourier feature model. The point is, I can make my model now as rich or as sparse as I want using all 15 Goyal-Welch variables. If I want to have a model with p equals 1, fine. I'll just produce one of these random features. If I want to have a model with 10,000 predictors, all right, I'll combine and nonlinearly transform the Goyal-Welch predictors 10,000 different times. This is not such an adventurous idea, it turns out. This is a neural network. It's actually a really simple neural network. It's a one-layer neural network. I take my original Goyal-Welch data, I propagate it through one node. That's this nonlinear transformation. I propagate it through a different node. That's my second feature. And I can have as many nodes as I want in the middle. The bigger the number of nodes I have in the middle, the better the approximation. That's called the universal approximation theorem. People like Hal White worked on those ideas in the 80s. This is exactly the underpinnings that align very closely with the theory that we have here. We can do it in the data just as easily. So I'm going to do this. I'm going to take the 15 Goyal-Welch predictors. I'm going to produce a model that might have one predictor in it, might have two predictors in it, all the way up to 12,000 predictors in it. All right, so very complex models. Now the other point that I'm going to make here is that I'm going to be looking at very small training sets. The number of observations that I'm going to train my model on and the results that I show you here is going to be 1 year of monthly data, 12 observations, t equals 12. But I'll estimate models with 12,000 predictors. So the complexity C is 1,000 in those models. I'm going to go up to C equals 1,000 and everything in between. Why do I want to do this? Well, in the paper, we have a lot of other t that we look at as well to show you that it's not just about t equals 12. The point here is with t equals 12, I can actually get to extreme model complexities with a relatively small p. If I made t 1,000, then I really have to ratchet up the number of observations I have to get to truly complex models. The other point that this allows me to make is that you get this virtue of complexity even in really small samples. All right. So let me show you what the empirical plots look like. Panel A, I'm showing you the plot for the expected return. Panel B, I'm showing you the plot for the volatility of a trading strategy based off of these predictions. And panel C is the out-of-sample Sharpe ratio. These are all out-of-sample objects. For each tick mark on this axis, that's a choice of P. That's a model size. I estimate a model with that number of parameters. I do it in a rolling 12-month window, forecast 1 month out of sample, and build a trading strategy designated to exploit that forecast. And what do you see? Well, if you use p equals 0, just a constant in the regression, what happens? The expected return of the strategy is 0. On average, it's 0, as you would expect. What happens as I start to increase model complexity? The ER rises monotonically. And what's going on with the volatility of this trading strategy? Well, notice that the scale is really skewed here because I went to such extreme degrees of model complexity. But when I get to 1, the volatility of the trading strategy blows up, just as the theory predicts. But when I push beyond that, the volatility mitigates. Why? Because I'm doing implicit shrinkage by always trying to pick these low variance betas via ridge regression. The final point is, of course, that what we see is for this entire spectrum of complexity, you see essentially a continually increasing Sharpe ratio. In the data, it eventually flattens out somewhere between C equals 50 and C equals 990. Increasing the size of your model increases the out-of-sample performance of these models. These are data plots. They have a strikingly close correspondence with the theory we just looked at. All right, the last thing I want to show you is what do these timing bets look like? So the timing bets are actually just the predictions, the ERs, right? The return forecasts that come out of my model. Here's a time series plot from 2 of the models. Let's just, for simplicity, focus on one of these. Let's focus on the red line, all right? So you're going to notice a couple things. First of all, the market timing strategy that you get from a model like this is long only. It does one of 2 things. Either it invests 0 in the market or it invests a positive amount, which is really kind of striking because brilliant guy John Campbell said, if you want to make predictors work in return prediction, what you should really do is put weak restrictions like not allow your expected returns to be negative. Well, this machine figured out to do that, but I didn't tell it, right? It just used the data to understand that taking short positions is not a good idea when you're doing market timing. The other point is that where does the performance come from? It really comes from the fact that the machine figures out when a recession is going to happen. All right, so there are 15 recessions in the sample. You'll see that the weight in the market drops off leading into each of these NBR recessions. All right, that's where the out-of-sample performance comes from. Okay, we have a number of extensions. This is part of a big research agenda. We look at lots of different asset classes, international equities, bonds, commodities, currencies, interest rates. We look at the cross-section of stocks. This was the time series, the univariate market timing problem, essentially. We do the same thing in a panel setting. And we've looked at deep versions of these models. So I showed you a 1-layer neural network, but you could stack these things on top of each other and make deep neural networks out of them. All right, so I want to conclude with a couple of remarks. First of all, asset pricing and asset management. Obviously, the reason why we're having this conference is because these areas are in the midst of a boom in ML research. All right? So I told you I wanted to make the case for why we should be doing financial machine learning. I think the first step in making that case is to provide a rigorous theoretical understanding of why big models can and do work. All right, so hopefully I've made progress on that here. I would note that this is not a license to throw a whole bunch of random arbitrary predictors into your model. Absolutely not. Instead, it's an advice to include all plausibly relevant predictors. But don't just put them in linearly. Instead, use rich nonlinear models rather than simple linear specifications. If you follow this recipe, the theory tells you it's going to give you prediction of portfolio benefits. All right. Now, the last point I want to make before I wrap up comes back to my first slide, which is talking about George Box. Okay, so I have 2 quotes here from Box. Absolutely brilliant statistician, really heavily influenced the way a lot of us think about the world. First quote many of us have heard before. All models are wrong, some are useful. Great point. What is the point of that? All models are misspecified. We never can figure out the correct way to specify a model. So that thought experiment that I started off with, where the analyst is trying to figure out how they should specify their model, they have to use an approximating model. Because even if they think they're specifying it correctly, they're wrong. Second point, since all models are wrong, the scientists can't get a correct one just by excessive elaboration. Quite to the contrary, following Occam, we should seek economical descriptions, the principle of parsimony, right? The ability to devise simple but evocative models, that's the signature of a great scientist, right? And if you over-parameterize, that's just a sign that you're mediocre. Okay, so we call this Occam's razor. I have this question mark after Occam's blunder, right? So just to lay out the logic very clearly, small models are preferable only if they're correctly specified. Everything that I said here would go out the window if the true model had 3 predictors and you knew exactly that model and you never had to approximate it. But we never know the truth, right? Well, if that's the case, I think I just proved to you that you should always use the biggest possible model if you have a misspecified model, the best approximating model. So what's the logical conclusion? I think we have an argument at our disposal for doing big models when we do machine learning in finance. All right, so I'll wrap up with that.